In the second optimization problem, we are told that two posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be secured by two wires attached to a single stake running from ground level to the top of each post. Then we are asked, where should the stake be placed to use the least amount of wire? Okay, so the first thing we have to do is draw a diagram of the situation. So then we have to find a primary equation. W equals amount of wire, and the amount of wire, looking at the diagram, would be Y plus Z. Then we have to find a secondary equation that can be used to change the primary equation into a single variable. In this case, it would be the Pythagorean theorem, but we would have to do two. One for this triangle to find y in terms of x, and one for the bigger triangle to find z in terms of x. So we know that y squared equals x squared plus 12 squared, and that means that y is equal to the square root of x squared plus 144. The other one, z squared equals 30 minus x squared plus 28 squared, which means that z equals the square root of 30 minus x squared plus 28 squared. Then we have to substitute these constraints into the primary equation. W equals y plus z. Substitute y, the square root of x squared plus 144, and you substitute z, so plus square root of 30 minus x squared plus 28 squared. That gives us that w is equal to square root of x squared plus 144 plus the square root of x squared minus 6 dx plus 1684. Afterwards, we have to differentiate w. So w prime would be equal to x squared plus 144 1 half to the 1 half plus x squared minus 60 x plus 1684 all to the 1 half. So when we differentiate, this 1 half comes to the front. We've got x squared plus 144 to negative 1 half times the derivative of the inside, which would be 2x, plus this 1 half comes to the front, then the inside stays the same, 100 to the negative 1 half, and that times the derivative of the inside, which is 2x minus 60. We can do some cancellations here. We know that this 1 half and this 2 are going to cancel. So now we can set the equation equal to 0. Then we solve for x. So move this to the other side, we get that negative x over the square root of x squared plus 144 is equal to x minus 30 over x squared minus 60x plus 1684. We cross multiply, we get that negative x and the square root of x squared minus 60x plus 1684 equals x minus 30 and the square root of x squared plus 144. Then we squared both sides to get rid of the square root. We find that x squared times x squared minus 60x plus 1684 is equal to x minus 30 squared times x squared plus 144. When we simplify, we get that 640 x squared plus 86 x minus 1029 equals 0. Notice that I moved everything to one side and set the equation equal to 0. Now I'm gonna factor. So 320 parentheses 2x squared plus 27x minus 405 equal to 0. We can factor even further, so 320 parentheses x minus 9 parentheses 2x plus 45 is equal to 0. So now we form two mini equations and we set them equal to 0 to solve for x. So x minus 9 is equal to 0 and 2x plus 45 is equal to 0. We solve for x, get that x is equal to 9. We solve for x here, we get that x is equal to x equals negative 45 divided by 2. However, since length in the real world cannot be negative, we cancel this. It's irrelevant, and we're left that x is equal to 9. I mean, that would be the position away from the first or from the smallest post that we would place a stake. But we want to know how much distance that would be, so we plug in that into the equation, and okay, so w of 9 equals 9 squared plus 144 plus the square root of 30 minus 9 squared plus 1684. And when we simplify this, w of 9 equals 50 feet. Still, the question asked how far from the post should we place a stake, and the answer would be 9 feet away from the shortest post. And that's our final answer.